Howdy, howdy. This is Mr. Potter. We've been discussing derivatives, instantaneous rate of change for quite a few lessons now. And one of the things that we've noticed is that it tends to be a tedious process. The idea of having to evaluate the limit, simplify the limit algebraically, and then finally resolve the limit takes a lot of time. And so the question often arises, what's the practical use of a technique that really takes so long to process? And so what we're going to be talking about in this section are some basic rules that we can follow to help expedite this process. The idea is that if we recognize some patterns in the process of evaluating these limits, that we will have rules that we can use to make taking these limits and finding the derivative functions much quicker. So we're going to start off with some really basic rules just from behavior that we recognize from different functions. So let's say that I have a function y equals a constant. One of the things that I notice is that no matter where I draw this constant, this horizontal line will always have a slope of 0. And so the question is, okay, well, if I always have a derivative of a constant, do I always end up with 0? And so we can show this by taking the limit of an arbitrary constant. So if my function is defined to be k, then my derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. And we're going to evaluate this limit for this particular function. So this becomes the limit as h approaches 0 of my function, which is k, minus my original function, k, over h. And so what I end up with is I've got the limit as h approaches 0 of a constant 0 over h. And so this is really 0 times this limit. But because this is a constant 0, no matter what this function does, this function is always going to be 0. And so my derivative ends up being 0. So our first of our rules for differentiation is the idea that if y is some constant, then the derivative is going to be equal to 0. The next thing we notice from the behavior of our parent functions is whenever I have a line y equals x, I notice that the slope of this line is always 1. And of course, this comes from algebra when we think of this in our slope-intercept form. That the slope is always going to be 1. So the question is now, okay, can we prove that this is always going to be the case? And these are going to be some of our basic steps that we'll be using to prove about derivatives in general. So I'm going to let my function be x. And so if I'm trying to find the derivative, that's going to be equal to the limit as h approaches 0 of my function evaluated at x plus h minus my function evaluated at x all over h. Well, if f of x is x, then f of x plus h is going to be x plus h. And so this limit becomes the limit as h approaches 0 of x plus h minus x over h. And I notice that I have a 0 pair here and here, so those will subtract out, leaving the limit as h approaches 0 of h over h. And with a common factor in the numerator and denominator, I end up with the limit as h approaches 0 of 1 over 1. And so that means that no matter what happens, whenever I'm dealing with y equals x, my constant rate of change, my instantaneous rate of change, is going to be a constant value of 1. And so this brings up some interesting ideas, because if I was to make this y equals 1x plus 3, just translating this line up or down doesn't change the slope of the line. And so the idea of adding two functions together should have some very predictable effect on the derivative. And so the next thing I want to take a look at is, well, what happens if I have a constant in front of my function? I've got this constant in front of my function. This should affect the slope by just multiplying by that constant. So if I was to have the line y equals 3x, that should have a slope of 3. If I have the line y equals negative 5x, that should give me a slope of negative 5. So again, f of x is going to be some arbitrary function. But what I'm going to do to find the derivative of this function is still set up my limit. It's going to be the limit as h approaches 0 of my function at x plus h minus my function at x, all divided by h. And remember that my function is a constant times f of x plus h. a constant times f of x. So this is really a constant that I can withdraw completely out of my limit from the properties of limits. And because I can do that, this limit that I have left, no matter what f of x happens to be, is defined to be the derivative of f at x. And so what I end up with is I end up that the derivative of a constant times f of x, this derivative is going to be equal to a constant times f prime of x. And so now this is actually going to help us in our next step. So what I want to do is I want to talk about your generic polynomial term, the derivative of x to the n power. And I want to know, is the derivative of x to the n something predictable? And I'm wagering that it's going to be the c times x to the n minus 1. Actually, it's going to be n times x to the n minus 1 power. So let's talk about this. The first thing that I want to talk about is we are going to be dealing with x plus h raised to the n power. And so we are going to be expanding this binomial. So I'm going to have my first term, which is x to the n, plus my second term, which by binomial theorem is going to be n times x to the n minus 1 times h to the first. My second term is going to be n times n plus 1, n minus 1 over 2 x to the n minus 2 h squared. My next term is going to be n times n minus 1 times n minus 2 over 6 x to the n minus 3 h cubed. And this procedure is going to continue until I eventually reach h to the n power. So the coefficients will follow the Pascal's triangle, the combinations that we learned back in pre-calculus. The powers of x will decrease starting at x to the n power and decreasing until I reach x to the 0 power in the last term. And my powers of h will increase starting at h to the 0 for the first term and leading up to h to the n. So using the definition of a derivative, if I want to find the derivative of x to the n, that's going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, which ends up being the limit as h approaches 0 of this. So I'm going to have x to the n plus n times x to the n minus 1h plus n times n minus 1 over 2 x to the n minus 2 h squared. And then I'm going to have n times n minus 1 times n minus 2 over 6 x to the n minus 3h cubed plus, and this will continue all the way out till I reach h to the n power, minus my original function, which is x to the n. And all of this is being divided by h. Now remember, the process that we follow to find these derivatives are very consistent. The first thing that we want to do is eliminate these terms that add up to 0. So I have an x to the n power and a minus x to the n power, and they make a 0 sum. And every term that's left has a factor of h, including all of these terms. I can imagine factoring out an h out of that numerator, and so I end up with h times n times x to the n minus 1 plus n times n minus 1 over 2 x to the n minus 2h plus n times n minus 1 times n minus 2 over 6 x to the n minus 3h squared plus dot 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 plus h to the n minus 1 power after I factor all of these h's out. And of course, the reason I'm factoring all these h's out is because I have a common factor in the numerator and denominator. H goes into h one time. And so I'm left with the limit as h approaches 0 of this parentheses, which is n times x to the n minus 1 plus n times n minus 2 over 2 times x to the n minus 2h plus n times n minus 1 times n minus 2 over 6 x to the n minus 3h squared plus all the terms to h to the n minus 1. But if I'm taking the limit as h goes to 0, if h is 0, this term is 0 times some power of x. This term is 0 times some power of x. And this term is 0 times the 0th power of x. And so the only thing that I actually have that doesn't involve h anymore is n times x to the n minus 1. And so what that means is that if I want to take the derivative of some simple polynomial terms, I want to take the derivative of x squared. Its derivative would be 2 times x to the first, or 2x. If I want to take the derivative of x to the fifth, that's going to be equal to 5x to the fourth power. And this works for what we already have. I know that x to the first derivative is supposed to be just 1, but this should be equal to 1 times x to the 0 power, which is 1 times 1. And if I'm dealing with x to the 0 power, and I want to take its derivative, I should end up with 0 times x to the n minus 1 power. So this would really be just minus 1. And 0 times any constant should just be 0. So these agree with rule 1 and rule 2 that we talked about earlier. But I've got the more general form that if I have any polynomial term in x, I can take its derivative just by decreasing its exponent and changing the coefficient to be multiplied by its original exponent. What rule 3 offers is that if I want to take the derivative of 3x squared, it should just be 3 times whatever the derivative of x squared is, which we saw was 2x. And so this gives us 6x, which essentially means that whatever this exponent was, I can multiply times my existing coefficient to find the new coefficient of my derivative. And the exponent just follows the same rule. It decreases by 1 from 1 to it was. So the last of these rules of differentiation that I want to talk about is because I'm talking about polynomial terms, it sure would be nice if adding derivatives together gave us that same property. So the idea is that the derivative of a sum is it equal to the sum of two derivatives. So that means that my function that I'm dealing with is really f of x plus g of x. And so my function evaluated at x plus h should be equal to my original f at x plus h plus my original g at x plus h. And so I'm looking for the limit as h approaches 0 of f of x plus h plus g of x plus h. This term minus this term f of x plus g of x. all divided by h. And addition is commutative, so it doesn't matter in which order I bring these terms. So I could have f of x plus h minus f of x, combining these terms together, and then combining these terms together, adding g of x plus h minus g of x. Again, the limit as h approaches 0. And all of this is being divided by h. But this is two fractions. So I'm really dividing each of these terms by h. And this limit ends up just being the derivative at f. And this limit ends up being the derivative at g. So we do have the property that the derivative of a sum of two functions is equal to the derivative, the sum of each of the two functions' derivatives. And because of that rule 3, the idea that we can do a constant times a function, I could make this a negative 1 times g, and I could subtract the terms. And because of what we learned just a few minutes ago with rule 4, the idea that the derivative of a polynomial term would be equal to n times x to the n minus 1, I now can approach taking the derivative of virtually any polynomial. So, what this gives us, the idea is that I could have some function like f of x equals 3x squared plus 6x plus 7. And this is really 3 times x squared plus 6 times x plus 7 times 1. And from the rules that we've learned, if I want to find the derivative, rule 4 tells me that I can just take the derivative of each of these and just add them together. Rule 1 says the derivative of a constant is 0. Rule 3 says that the derivative of a constant times a function is going to be a constant times the derivative of the function. And the derivative of x is 1 from rule 2. And the derivative of a polynomial term uses that n times x to the n minus 1 power. And so what I've got here is I've got the derivative of my original function is 6x plus 6. And so this represents the instantaneous rate of change. This represents the slope of the tangent line. at a particular function value x. And I can take the derivative of any polynomial as long as it follows these rules. I can take the sum or difference of derivatives. I can take the lead coefficient, and it's just the coefficient times the derivative of each function. And we've talked about some of these special cases for the polynomial and also the more general term. So let's do one more example. Let's say that I've got my function is y equals 6x to the 4th plus 4x to the 6th plus 3x plus 17. If I want to find the derivative, what I'm going to do is take the derivative of each term. So this would be 4 times 6, which is 24, x to the n minus 1, so x to the 3rd power. Here I've got 16 times 4, which is 64, x to the 15th power. This is really 3x to the 1st power, so I'm going to have 3 times 1, which is 3, x to the 0 power, which of course we would write as 1 times 3. And this is a constant. This is really 17 times my constant 1. And so the derivative should end up being 0. So I know that the derivative of x is equal to 24x cubed plus 64x to the 15 plus 3. So I've got a very simple way to take the derivative of any polynomial function. And as we go through this chapter, we'll talk about how to deal with some of our more esoteric functions. In the next part of section 3.3, which we'll talk about tomorrow, we'll talk about how to deal with situations when I'm dealing with the product of functions or the quotient of functions. Because these behave slightly different from the rules that we've learned so far. But it's not an unpredictable difference. It's something that we can actually do quite precisely. And we'll talk about that tomorrow. So once again, this is Mr. Potter. Thank you for watching. Have a great